Hi guys, it's Simon here. Welcome to this new AI Radar. Today I'm gonna talk about computer vision and machine learning for the sciences. Meta has released a new multimodal AI model called ImageBind, which acts as an open source framework for eventually creating complex scenes and environments from one or several inputs. The model currently works with 6 types of data, including text, visual, audio, depth, temperature, and movement. ImageBind gives machines a holistic understanding that links objects in a photo to their corresponding sound, 3D structure, temperature, and motion. The application of ImageBind could include enhancing search functionality for photos and videos or creating mixed reality environments. Although ImageBind is still in the early stages and has not been released as a product yet, Meta plans to expand its data modes to other sensors in the future. Let's try it out. For example, if fed a picture of a tiger, ImageBind could retrieve its roars. Sounds like a horse. Sounds more like Similarly, if given a picture of a dog along with the photo of a beach, the system could produce an image of both. Lovely. It looks very likely and natural. A collaborative research team from the MIT Takeda program has developed a novel AI-based estimator for manufacturing medicine that uses physics and machine learning to characterize rough particle surfaces in pharmaceutical pills and powders. By illuminating particles with a laser during filtration and drying, the researchers are able to measure particle size distribution and determine whether the compound is adequately mixed and dried without stopping the manufacturing line. The process is more secure and efficient than current standard operating procedures, and the machine learning algorithm requires less data for training due to the unique combination of physics and machine learning. Storing and sharing increasingly large datasets is a challenge across scientific research and industry. Baler is a machine learning based compression tool for scientific data that uses autoencoders. It trains a machine learning model on data, compresses the data using that model, and then decompresses it using the model at a later time. The tool has been developed by researchers at Lund University and the University of Manchester and shows promising results for the compression of high-energy physics data and computational fluid dynamics toy data. Baler provides an easy way to compress and decompress datasets and plot the performance of the compression decompression, as you can see here from the example. The HEP autoencoder used in the tool consists of 3 fully connected neural network layers in both the encoder and decoder. You can find the Baler package on Github and the related paper on the preprint server archive.org. Baler, a machine learning based compression of scientific data. Researchers at various institutions present FWX, a Python package with a new implementation of artificial intelligence autoencoding algorithm used as an ultra-fast and efficient anomaly detector built with a forest of deep decision trees for field programmable gate arrays to be used in high-energy physics. The autoencoder in the tool is trained using non-physical processes of the standard model, and it helps identify unknown and undiscovered beyond the standard model processes. The tool is then deployed in real-time trigger systems for anomaly detection of new unknown physical processes, such as the detection of exotic Higgs decays. The design results in ultra-fast and ultra-efficient FPGA implementation with minimal reliance on digital signal processors. The tool offers anomaly detection at the lowest latency values, 25 nanoseconds, a nanosecond being a billionth of a second, for edge artificial intelligence users with tight resource constraints. As you can see here, the researchers published their approach and findings on archive.org. Here you have the paper, nanosecond anomaly detection with decision trees for high energy physics and a real-time application to exotic Higgs decays. Miles Cranmer, an incoming assistant professor at Cambridge University and research fellow at Simons Foundation, has released an open source package called PySR, which aims to democratize and popularize symbolic regression for the sciences. Symbolic regression is a very interpretable machine learning algorithm for low-dimensional problems. The tools search equation space. These tools search equation space to find algebraic relations that approximate a dataset. PySR is a Python front-end API in a popular style of the scikit-learn machine learning library, built on a high-performance distributed backend and interface with several deep learning packages. The internal search algorithm of PySR is a multi-population evolutionary algorithm designed for optimization of unknown scalar constants in newly discovered empirical expressions. The package is capable of performing automatic differentiation and distributing populations of expressions to thousands of cores across a cluster. PySR's backend is built on the extremely optimized Julia library, SymbolicRegression.jl. The main objective of this package is to discover human interpretable symbolic models. It is based on a philosophy where the definition of simple expression is the one that is most interpretable by the user. Complexity in PySR is equal to the number of operator nodes in an expression tree, regardless of each node's content, and it's completely user configurable. Cranmer has posted a paper on archive.org with PySR's implementation details and philosophy approach. In practice, once you have installed the package, you write the relation you wish to model upon data, create a PySR model, and train it for a certain number of iterations you can specify. The resulting search code contains hundreds of thousands of notations and equation evaluation. By calling the usual fit function, you launch a Julia process which will do a multi-threaded search for equations to fit the dataset. equations will be printed during training, and once you are satisfied you can quit with early stopping. The author also introduces a new benchmark called empirical bench to quantify the applicability of symbolic regression algorithms in science, which measures the recovery of historical empirical equations from original and synthetic datasets. The author's results indicate that classical algorithms based on evolution and other untrained symbolic techniques, including PySR, outperform pure deep learning based approaches such as EQL and SRT transformer in discovering historical empirical equations from original and synthetic datasets. DAO hybrid methods like generative models, reinforcement learning methods, and symbolic distillation have the potential for improving symbolic regression, says Grammar. You can see you can find the package, both the packages PySR and SymbolicRegression.jl on GitHub. Okay guys, I hope you enjoyed the video. If you like it, please hit the subscribe button and subscribe to my channel. It's all for today. See you next time. Bye.